Welcome to Answer Everywhere. We are taking a second look at the Kissat sat solver. In our first look, I realized that I had a hard time reading the code. That was, I think, dependent on two factors. One is that it's an unfamiliar area for me, sat solvers, and the other is that the code organization wasn't organized kind of the way I expected for like I guess what you might call like a scientific optimization library. So it was difficult figuring out context clues. I think at the time I had promised to, when I took a second look, to have read the papers. And I have not read the papers. I did watch some talks. I did look at some material. So I know slightly better than nothing, which is what I knew going into the last one. But we will hopefully learn a little bit about how sat solvers are built. We probably won't learn a ton necessarily about how they work deep under the hood. And so let's dive in. So last time I had said something to the effect that given conjunctive normal form, probably, or perhaps one way that we want to do this is that we can just split it on the ands and do it in parallel. That's, I realized after I stopped that's wrong. There is this structure, and it is true that you can split it up, and the conjunction is false if and only if the individual or clauses are false. However, I realized that you don't have the kind of like optimal substructure that you would want for a dynamic programming problem, because you can always add one clause at the end that falsifies like the whole thing. Like you can say, I want a car that's you can sell for under 80 grand and uses some amount of aluminum and has a top speed of this and follows safety guidelines and also can fly like an airplane. And that last clause, because it references variables from over here, the car, can make everything false. So if you had split up the problem and tried to solve it in parallel and then group the hypotheses back together, there would not be enough. The existence of one change, like a 1-bit change, can be so fatal that you would not want to do that. And so it seems everyone seems to have landed on the conflict-driven clause learning algorithm. There are other tricks that are used, but the basic idea, kind of going into this, that we're going to assume is that the way that you solve these is you choose a variable like A, you set it to true or false, and then you on the fly create a decision tree. Like if A is true, then what happens if B is true, and what happens is if B is false, and that creates two branches of the decision tree, two kind of possible worlds. And the kind of main algorithm we should have in mind as the kind of the default is that we're just going to do depth first search with backtracking over this branching tree of what you might consider different variable assignments or different possible worlds. And then CDCL and other algorithms are going to be a refinement upon that. And I don't know how deeply we want to go into this, but we'll set it there, and then as we look at the code, it may be worth going into like more depth on any of those particular things. So with that in mind, so we have Arena, which is going to be, I assume, about allocators. I know that at least one of my followers, Bot Eater, is interested in allocators. So I'm tempted to jump in there, but in the interest of making this of interest to people who are mostly interested about sat solvers, I'm not going to do that. But let's try to find maybe an entry point. I guess I will do Emacs. And let's see if we can find something like, can we just visit the tags file? How terrible is it? I think I just deleted it. But let's try to find like tree. Actually, GitHub search is going to be better for this. How about database or DB? How about DB? There's DB as in debug. Statistics, strength, and deduce. What about database? No. What about, let's look at structs. We saw some of the structs before. So here's a proof. Okay, so there's watching. I think watching shows up maybe in the more fiddly bits of the sat solver algorithm. That's maybe like on the more, like a deeper dive. Walking, I think, is going to be about walking the tree structure. And that file might tell us about what the main tree structure is called. Trail might mainly be about keeping a list of, you know, things that we've checked. All right, great. Thanks, Giovanni. Statistics, this might be for profiling. For building sat solvers, that might be important. Sort, I'm going to ignore. Resources, resolve is probably important. Resize, that could be memory related or sat related, but I think I'm going to ignore it. Prop lit, this is probably literal propagation. Prop search, prop dense. And we looked at phases before here. Lucky, this might be lucky guess. I guess let's look at main. People are always asking me to look at main. And I'm usually telling them main is rarely as cool as you think it is. But I think here, main is actually somewhat cool. Or maybe not, I don't know. Okay, it's going to initialize an alarm, which I forget, but I think I assumed last time was just to like let it know when it found a satisfiable, you know, whatever, basically end the walk. It's going to initialize signal handlers, and then we've got this application. I can't jump to here, although maybe I can over here. Well, that works. So this is the header. Do we get application.cc? Let's just go straight to the source directory. Application.c. We're not in C++, I guess. All right, then we have init app, which is just basically zeroing out things that need to be zeroed out, and it's printing some stuff. And that looks like command line parsing. I'm just like very quickly looking at stuff. This is going to be, you know, the command line flags and everything are going to be set up for people who work on sat solvers. I think primarily people who are doing this for sat solver competitions, and also for the industry and stuff. I don't know which one is, you know, I don't know how often people actually invoke sat solvers in industry. Like if you're designing a chip, I don't know if it's invoked like over and over again, or only once you get to a certain stage of design. Here we're parsing the input. Let's look at I think GitHub will hopefully give us the names of functions. If. Oh, it's confused because of the if-def structure. Maybe the large number of if-defs are why it can't find, why the C-tags parsing doesn't work. And this is not really helpful. Let's actually go back to the proof, because I think the proof told us that if I remember correctly, the struct of the proof told us some of the important types. So for example, the Kissat struct is like the kind of God struct, I think. In fact, that must be the important struct, right? Is there any chance we can jump to it? Yes. Okay, so compacting. I don't know what I don't know from what I've read what backbone and computing are. Sorry, about what backbone and compacting are. I have guesses what they could be. Inconsistent. I don't know if this means the whole problem is inconsistent, and if so, why you? It seems like you'd want to sound an alarm, but I don't know. Extended is maybe whether we've extended the original problem with more clauses. And that's going to be a general feature. So the setup is, I guess I'll assume that you're in a SAT solver competition. You get some number of SAT problems that are in this kind of archaic text file format. And the format specifies what the variables are and what the conjunctive normal form clause structure is. And that's like the starting world of the SAT solver. And those are put into some sort of structure, which you might call a database, maybe, I don't know, an array or a table or a heap or something. And then what conflict-driven clause learning does, the learning part is from as it makes life easier by adding additional information. The information is somehow encapsulated in the original problem, in the sense that if you take the original problem and you apply the rules of logic, you can deduce other clauses that are also true in any world where the original CNF problem, I guess, is satisfiable. Or I don't know if the reverse is also true. But at any rate, so the assumption is that, like, if we're going to satisfy it, if there's a satisfiable part, then we can add these clauses and we are no worse off. We've added additional stuff to our database on the one hand, so it's larger, and maybe that's bad. On the other hand, we've given more structure to the search space, and that structure is used to efficiently solve problems. So it may be the case that extended is just tracking whether we've extended the initial clause set. I don't know what iterating and preprocessing are, and I'm also not sure about probing. And then warming and watching, I still don't know. Okay, but we have vars, which I'm going to guess, since it's unsigned, is just the number of vars, although they might be packing the variables in to some integer, like bit vector style. And then we have size, active, and I think randec is just some random thing. And then we have some assigns. We have a pointer to an assigned array, a pointer to some flags, some marks, some values, and some phases. Eliminated, I don't know what the struct is there, but presumably things that have been eliminated somehow. Links and a queue and some heap. So we've got both like memory management and also like logic stuff kind of commingled in the same struct. And there's a schedule, which is a heap. I'm not sure really what goes on the schedule heap, possibly clauses and some scoring stuff. And we have a conflict clause, which is going to store, if I understand correctly, as you're going down, there is a conflict clause, and we'll look at this, I think, in a moment, but you essentially have one conflict clause at a time. And that's kind of like from the perspective of the programmer, that's state in the program. And then you finish kind of doing what you're going to do, having observed that conflict clause, and kind of restart is I think more or less what's going on. And this looks like more memory stuff, arena, etc. Bounds, classification, node, tick, resolve, gate, sweep, incomplete, profiles. Okay, so I don't see an explicit tree here, although it is maybe one of these arrays. So let's go back here. Possibly links. Possibly value assigned. I don't know. And we have some functions. So if you call Kissat assigned, it's going to look at all of the vars and subtract off the whatever the solver believes is unassigned. So I'm guessing the vars is a count of the variables, and solver unassigned is a count of the unassigned. Otherwise, I don't think that subtraction doesn't make sense for as like a set difference in C. It would make sense in Python, but this is not Python. And vars is just solver vars. So vars seems to literally just be an integer counting the number of variables. All literals is what? This is, so unsigned lit is equal to 0. I'm not sure what this syntax is. And equals lits. Lit not, oh, this looks like it's walking a linked list and incrementing the lit variable. And so I guess that means all literals, so lit is an argument, right? I don't know how this is called, but somewhere lit must be storing, oh, lits. Okay, so the number of literals is 2 times the number of solver variable. So why 2 times? Because we have both the negation, sorry, we have both the original variable and the negation of each variable. So I'm learning a little bit as we go about what is going on in the code. Here's my water. So for all clauses, we have clause star C equals the begin stack. Okay, so we look at the solver arena. So we're just looking in the memory, I think. And we're considering that the beginning of the stack, and we're casting that as a clause star, I guess it pointed to a clause. And somehow we're getting to the stack of the end of the stack. I'm assuming here stack means really an array, like a linear piece of memory as opposed to like a, oh, I guess that's what a stack is. I was thinking heap. Never mind, forget that. So we're going to the end of the stack and just, I think, counting stuff, right? Or, no, I think we're, not, I'm sorry, not counting stuff. I think we're actually grabbing all the clauses. Let's just verify this. This is something that is small and verifiable. Let's assign it to DeepSeek. I'll say, what's going on? Whoa. What's with the double hashes? I think that this is probably just standard. What's the word? C macro stuff that I just haven't learned. And I assume begin stack and end stack are things that are defined by Kissat. So the macro all clauses is designed to create a loop. Yes, we understand this. When you write all clauses my clause, the preprocessor will replace C with my clause, concatenate my clause with end, underscore end to form my clause end, concatenate my clause with next, underscore next. And so this is what DeepSeek is saying the end substitution is. Is that right? Is it different from the current? And that seems to be literally what is already there. Okay. So you do like all clauses of C, do something with clause C. Oh, okay, wait. Which would expand to for clause star C equals this. So it says it's expanding to a for loop. But where's the for? So basically this is a using C macros to create like a for each kind of structure, potentially. Yeah, it says similar. I don't know if I fully believe what DeepSeek is saying, but I guess. No, I'm going to ask Gemini. With even the same misspelling. So the hash is to concatenate two tokens. And so my clause and this allows the macro to create unique variable names based on preventing name conflicts. Okay. It also says it creates a for loop. So I'll ask it to give an actual expansion. I'll say in the for loop, have it print the clause each element to standard out. And while I was thinking, oh, okay. So define all clauses, blah, 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 type def clause, blah, blah, blah. Begin stack. So you have to define begin stack, and then end stack just is the pointer after the end of our clause. And so it's setting up the arena. Okay, so the for is just, you call it on for all clauses. So it's just setting up the middle part, I guess. Okay, I just wanted to figure that out because I thought I was maybe missing something more fancy about what the macro was doing. Okay, so that's that. And what does that tell us? That tells us that there's maybe not an actual tree structure. There may be just in this arena. Is that right? I'm not sure. Okay. And then what else do we want to know from this particular file? That gives us some stuff. I'll keep this file open. Search. Here's the search header. And now that I'm looking at it, I think that the headers of this program are maybe not so informative. Let's look at search.c. This is 220 lines. So there's something here. Okay, so start search. You give it the solver. It's going to call start on the search. It's going to call inc searches. I guess probably just doing statistics on saying that we've incremented the searches. What is init tiers? Is this important? This is like getting some options and stuff. Okay, so maybe that's a little bit, maybe we can black box that for now. And we're going to check if the options stable is 2. So this is going to be a Boolean. And so we're setting solver stable to whatever the value of this stable is. And then we're going to call Kissat phase, passing the solver and the search. Putting in get searches And we're going to print out, presumably, this is just some string as a part of an argument. It says we're initializing stable or not stable search after some either a stable search or a focus search after some number of conflicts. And then we're going to call init averages, passing the averages reference as a reference. And then we're going to call Kissat classify on the solver. And then if it's stable, we're going to init reluctant and update scores. And then we're going to init tiers, as in the, not like crying, but like a tiered hierarchy. And then we're going to init the limits. And then we're going to get a seed, which you can pass in as an option, I assume, because if you don't pass the seed in as an option, you can't reproduce your runs. And so I guess this is seeding the random number generator. And if we're not quiet, then I assume this is going to print out stuff like the limits and stuff. And what if we are quiet? Then we are somewhere down here. And it's also maybe generating some reports. Is it? Wait, what? So if we're, Oh, you know what? If quiet is not defined, yeah. Then what? I guess we're just done. I'm not sure. So I'm not sure if we've actually run at this point, because we set this random seed, and then we say we initialize the random number generator with a seed. I guess if quiet is not defined, then we go down here, we get the limits, and we print out decisions and stuff, and we say we're starting search, and so on. And then now we're defining a new function, I think at the same level, that's going to stop. So I'm guessing that probably what is happening is that the Kissat phase is maybe in the background or on another thread, initializing the search, and this thread or whatever is just something. I don't know. But it does seem like we're doing work, like initializing the limits and setting the random seed. So who knows? So what else is there? So there's start search, iterate. Maybe you have to call iterate. There is searching. It's going to, I guess, you can call it on the solver and it will tell you whether it's searching. So if Kissat propagated on the solver is false, then we return true, and so on. Okay, so that's telling us what searching is doing. I'm guessing maybe you have to drive the search by calling iterate. No, that's just checking. So assuming, just ignoring this assertion, if you call iterate, we're going to set solver iterating to false and report 0i. Okay, and let's look at init tiers again. So this is like setting some variables like stable, etc. Okay. So slowly but surely we're unraveling bits of this. I think the next step is to look at the Kissat phase. These are calls to Kissat phase. Let's go here. Again, this is a header, so that's not so useful, but let's look up Kissat phase and try to find the definition. We have print. Maybe Kissat phase is not setting a phase, it's just printing information about it. Okay, so with that in mind, this is just a print statement. Maybe classifiers doing work. Kissat init limits. Let's look at Kissat classify. It's void and gives us, there's nothing really to it. Where did it go? But if we look at the C file, okay, so the classify is going to look at the solver statistics, and this seems like it might be doing work. So we're going to look at the clauses binary and the clauses irredundant and add them. And that I think is going to give us a number. And we're going to look at the small clauses limit. So we get this statistics object, and I think we are computing statistics. And then it'll say, if actual is bigger than or equal to percent, we'll say solver big is equal to true. Otherwise, solver big is equal to false. Okay, and then we print some stuff. Formula classified as having some total number of clauses. So this is the smaller versus large, and have so many binary clause fraction, blah, blah, blah. Okay. So classify, again, is printing stuff. Good. So where's start search here? And update scores, I'm going to believe, is not actually doing search work. And I think probably init reluctant is not either. And init tiers doesn't seem to be. And I don't believe init limits is. So where? I think this is something we can ask Gemini. So in this file, where when you call start search, many of the methods seem to only print collect statistics. Where do you think the actual work of starting the search process begins? And now that I'm typing it, I'm going to guess that the thing that I thought was a print statement is maybe we can think of it as emitting an event. And then something's going to watch the events, or watch the log, and use that as a reason to kick off the process. Within the central while not res loop. There's a thing called Kissat search. While not resolved, class conflict, Kissat search propagate. If conflict, blah, blah, blah. Okay. Hello, bot user. How it seems to be the solver struck to be more of a state machine. Yeah, I think that's true. As opposed to what, I guess. So what did it say? Okay, so Kissat search. What are the chances Kissat search is? Here we go. All right, so if you call it Kissat search on the solver, you got this report thing. Res is probably resolved, and if we are inconsistent, then or maybe res is result. If we're inconsistent, res is 20. If not res and lucky early, as opposed to lucky early. Then we call Kissat lucky on the solver. And I'm guessing that's going to do something silly. Not silly, but maybe like just a random guess. And then this is checking lucky late and some pre-processing. I guess lucky early means before pre-processing. Lucky late means after pre-processing. If we still don't have a maybe result, then we're going to call Kissat classify on the solver. Otherwise, we're going to call start search. And while there's no result, we are going to call search propagate. That's what I thought search iterate was going to do. It's going to do some sort of some sort of work, some sort of iterative work, I guess, and it's going to return a conflict, or possibly return a conflict, an optional conflict, essentially. And if there is a conflict, then we're going to analyze the solver with the conflict. Or I guess if there's no conflict and solver is iterating, then we're going to, okay, so iterating is like a state machine thing. I guess it really means like, should we be iterating? Because the next thing we do is call iterate on the solver. And I think I remember correctly from like 3 minutes ago, if you call iterating, it stops the current iteration. And so I guess this kicks off the next one. Or rather, maybe it sets some variable to false. I forget exactly what it did. And then if there's unassigned stuff, we say result is 10. I guess 10 means there's unassigned stuff left. Otherwise, if we're terminated, then we're going to break. And we pass in this search terminated thing here. Otherwise, if we are reducing, I guess this means like if we should be reducing, like the state, the next transition state is, I guess, reducing. This is like saying what the next state should be. This is making it, I guess, try to be in that state. And so on and so forth. Okay, this is I think the main loop. And I wish that it was clearer where this was before, but I guess Kissat search is a pretty good name. If we get all the way down here, we have Kissat decide. Oops. Okay. So what are some of the things that we can do? We have reducing. We can switch the search mode. We can restart. And we can reorder. And we have rephasing and probing and cut and eliminate. And I don't really have much more time. Wait, did I say cut? I think I said cut, but I didn't mean to say it because I wanted to look in the code for cut. And we're not going to find it. But now I think is a good time to look at the CDCL algorithm. So bot user saying it propagates the inputs through the logic and then returns where there's a conflict. Then if there's a conflict, it identifies, otherwise iterates over what? Good question. Somehow it's iterating over a directed acyclic graph or a DAG of clauses. Let's see if we can find an image file of a. Do I have a drawing program? No. I don't know if this is going to work. There's a huge amount of latency, but I think you build up something like this, where left branch means true and right branch means false. I'm not sure if I'm writing this at the right level of generality, but you have some tree you can imagine. And then over here you have some list of clauses like A or G or not A. I don't know, some clause. And the sort of thing you're doing is you're saying, like, let's assume A is true, then we have to make a decision about B. Let's assume B is true, then A, B, and D are true. Does that satisfy, is that satisfiable with respect to this list of clauses? And so on and so forth. And there are a couple of shortcuts here. This is a G, but let's say that let's say you have some clause A, B, C to make it more consistent with my graph, and there are ors between them. Then if you know A and B are false, then the whole conjunction, which is a conjunction of, I think traditionally they are all 3 long. I don't know if that's always the case for the SAT solver problems, but if you know A and B are false, then it's no use checking what happens if C is false, because that would make the whole problem, you're never going to satisfy the problem that way. So once you know A and B are false, you assume C is true. And I think that's what they call unit propagation. And so that's one way to cut down work. And then the other way is you find what is called a conflict clause, and we're going to look at that in a second. But I think this is the sort of thing it's iterating over, kind of like a decision tree of making variables, of making different assignments on variables. And it seems like the reduced expression based on yes, that's right. So it's like leveraging the structure of logic to reduce the amount of work you have to do for depth first search is one way to think about it. And so we start off the world in this conjunctive normal form thing, but there are reasons for doing that. For one, that you can convert to it. I think in linear time is a really easy conversion of any kind of standard first order logic problem to conjunctive normal form. But just having this conjunction of disjunctions leaves some of the original, we've lost in some sense some of the original structure that we could have used for computing, and we've gained other things. And I think one way to think about conflict driven clause learning and unit propagation is that we've converted it to this easier graph traversal problem, but having lost a little bit of the structure, our search space is now like bigger than it really should be. And so CDCL, I think, and DPLL are kind of ways of mitigating that a little bit. I don't know if that's quite right, but that's kind of intuitively how I'm thinking of it. And I'm realizing as I'm learning about, as I'm looking at this Wikipedia article, that this Wikipedia article is not great. So I think, for example, it uses conflict clause and doesn't define what it is. So let's ask, I guess, Gemini. In CDCL, what is the definition of a conflict clause? And about Yeater, I think you're right. Basically, it seems to be a conflict clause is like when you have a disjunction and you're somewhere on the tree where all of the assignments are false. And why that's a conflict, I don't know. It seems like it's unanimously false. So in the like kind of traditional meaning of conflict, it doesn't seem like it's conflicting. But probably where that came from is that if you assume that the original problem is true, has some solution, it's satisfiable, then a clause of all falses is like a contradiction to that assumption. So it's essentially we've gotten to a place in the search space where we've reached the contradiction. And so the old algorithm was like, okay, so let's jump one back up in the search space. And then the CDCL algorithm, I think, at least conceptually, says, well, we can be smart about where exactly we jump back to. We can kind of figure out what the first assumption we made that kind of, I'm not sure, like forced this conflict. And they try to find a cut in the graph somehow where that decision was made. And then like as another optimization, just to get out of bad parts of the search space, they will often just like learn all of the conflicting clauses, like everything you've learned along the way, you've learned about the problem, but they're going to completely restart from scratch and like go back to the start of the search space in some sense. And I think that's what they refer to as restarting. All right, so in the context of conflict-driven clause learning algorithm, a conflict clause is a new clause derived from a conflict, which is a state where at least one clause in the Boolean formula becomes false under the current partial assignment of variables. I think here partial assignment means like with respect to the full problem. I've been kind of like talking as if we are examining one area of the problem where we fully assigned all of the variables in some like subset of the problem. I think that's what it means by partial assignment. And this newly generated clause is then added to the original set to prevent the solver from making the same incorrect decisions in the future. At its core, a conflict clause encapsulates the reason for a particular conflict. When it assigns a truth value to a variable, it can trigger a chain of logical deductions, a process known as unit propagation. So this is where, if that draw thing is still open, where we know that once we've assigned all of the n-1 variables as false, the next variable has to be true, essentially. And the generation of a conflict clause involves analyzing the implication graph, a directed acyclic graph. Yeah, so this is the graph I think I was trying to draw that represents the causal relationship between variable assignments. The nodes in the graph are the literals that have been assigned a truth value, and the edges indicate which assignments logically implied others. Okay, no, this is a different graph. So the graph the implication graph here would be like A, I guess, is a node. I don't know how we know in the graph whether it's been true or false. But there will be like an edge from A to B if, A true implies B true or B false. I'm not sure exactly how they model it. When a conflict occurs, the implication graph is analyzed to find a cut that separates the sources of the conflict from the conflict itself. This cut identifies a set of variable assignments that, when taken together, are sufficient to cause the conflict. So this is in some sense like a minimal representation of the conflict, I think. And then by adding the clause to the formula, the solver learns a new constraint that was implicitly present in the original formula. Okay, so this is important. This is like, it says it exactly. I think that's the right way to think about it. You've learned a new constraint. The constraint was always there. You've just made it explicit, and now your problem is easier. And what they call non-chronological backtracking, I think what this means is traditionally you would backtrack, like you would go one up, and that would be chronological backtracking. You reverse your latest decision. The conflict clause is constructed in such a way that it becomes a unit clause after backtracking. This forces the solver to flip the assignments of one or more variables involved in the conflict, often at a much earlier decision level than the one where the conflict occurred. So I guess the way it's describing this is like, I was imagining like in code traveling some tree, and maybe it's just saying we don't have to like go back up to some part of the tree. Like we don't have to like chase pointers or anything. We just assign variables, and that like implicitly defines a part of the tree. This back jumping allows the solver to prune the search space more effectively. Okay, so this is good. It's like the expression A or B and not A. Yeah, I think that's right. Okay, so this is a good description. I mean, it's clear. It says what the definitions of what all the things are. What I don't know yet is like in the you say nodes are variables that have been assigned truth values. How do we differentiate if, like, say A implies B implies A and B are true or false? Do we add and not A and not B as separate variables. And then A true implies B false would be A implies not B. So this symbol always means a node is always true, and the implication always means implies the following node is true. Something went wrong. Gemini. I'm just going to assume that's the case. I'm sure there are other... Oh. The thing that went wrong is I'm being rate limited. Oi. I have unlimited Gemini on my personal account. I'm used to just having it be unlimited. But so I'm going to assume that that's more or less what it means. Or maybe we can look up implication graph. I can't. I spelled it wrong. Google search. Google such a ripoff. I don't know. I mean, maybe. All right. Having won the SAT race, I think I can now confess I still don't understand conflict generation. Okay, good. So here is some implication graph, and I see a negative x73, and I happen to know, just from having done the previous stream, that x73, you would never, in math, call a variable x sub 73. That's for computers. But I happen to know that like this allows you to, in like the CNF file notation, this allows you to just represent each variable by an integer. So the integer would be negative 73. I also happen to remember that negative means negation in that file format. So I think that this is saying that setting x73 to false implies x56. I don't know what the @ symbol is, but I think that I'm just going to take this to mean as evidence, not proof, that in the implication graph, a node always represents true, and implication always means this implies that this is true. Let's see if we can search for the @ symbol. At decision level 56. Okay, so good to know. Okay, so that is, I think, bringing a lot of this together for me. I have to go shortly, but at least we now know the main, what appears to be the main loop. Let's see if we can find what it's doing once it has a conflict. So when we call search propagate, it's going to populate this conflict variable with whatever our clause type is. And then if there's a conflict, we're going to call Kissat analyze. So we saw that a conflict should come from a thing that's all false, given where all the variable assignments are now. And then Kissat analyze, I'm not sure exactly what it's going to return, but it's going to return res, which I think is a result. And if we get down here, it says report search result. This is what Kissat search. So I'm not sure how often Kissat search is called, if this is called like recursively, or if there's another thing that calls this that like drives what happens next if we find a conflict and like add it. But let's at least quickly look at search propagate and Kissat analyze. And whatever I had open before, I'm just going to abandon because I have to go to an event soon. Okay, so see if we can find, no. Let's see if we can find Kissat. What was it? Propagate, I think. Search propagate. What do you mean? Okay, so prop search. I'm going to guess the header is useless. Just open the C file. Okay, so Kissat search propagate on the you call it on the solver, It's going to call start propagate, and then set the solver ticks to 0. And then we have some search propagate variable that seems to be an array of integers. And it says saved propagate. So maybe we're like saving some propagated state. And then we're going to call search propagate on the solver, which is different from Kissat search propagate. And we're going to get back the conflict here. And then we're going to update statistics and maybe have a trail. And let's see if we can find this. Okay, search propagate is going to call. Again, I'm going to get this propagate thing, whatever it is. And while we don't have a result, which is a clause, and it's set to an integer, so I'm guessing clause is somehow an alias for an integer. Let's see if there's like a struct. Type def struct. Okay, here, clause. Okay, so clause is a lot of stuff, including garbage, quotient, reason. So this is like maybe metadata about the clause. And I'm guessing these unsigneds are used as booleans. And maybe size is like how many literals are in the disjunction. Although maybe not, because we have unsigned lits as 3. So I guess it's assuming that everything is a size 3 clause. I'm not really sure what size is. Maybe size in the of memory or something. But among other things, I think this is probably keeping track of whether it's been visited, like you would do for certain graph searches. But at any rate, that's what a clause is. And so I guess this is just zeroing out the struct or something. And then we're going to call we're going to get this propagate thing. And while we don't have a result, which the result is a clause, and we're not at the end of the array, we're going to call it on the solver trail. We're going to iterate over whatever the end array of the solver trail. That's somehow the end of clauses that we're going to look at, maybe down to some leaf node. And then we're going to call search propagate literal on the solver, incrementing propagate, and potentially getting a result. And then we set solver propagate to propagate, and we return the result. Isn't that supposed to return conflict? Let's just verify this. What was it? Kissat search propagate? Yeah. Yeah, so somehow whatever the clause search propagate returns is supposed to be the conflict. Can I use back to go here? Maybe not. But it wasn't obvious to me that that's how we know that to be the case. I'm guessing it's just whatever search propagate literal is doing that is going to produce a conflict. Let's see. Search propagate literal. Define propagate literal. This is maybe the definition of propagate literal. Where are you? You pass in the solver, and maybe for probing propagation, this ignore thing, and a const unsigned literal, And we're going to search some stuff and log some stuff because I assume this is an important, this gets called a lot, I think, in a hot loop. So that's probably why there's like debug assertions and log stuff. It needs to be correct, and you may need it to be fast and stuff. Presumably it needs to be very fast. So the first thing we're going to do is get watches. So we're going to look at the solver, everything that is being watched, I think. And then we're going to get the arena. And the number, I think just the number of assigned, or maybe the whole, maybe like an array of the actual assigned things. Maybe assigned is just the pointer to the start of some array of assigned. I don't know. And then again with the values, I'm going to assume that these are actually the actual assigned variables and the actual values is how I'm going to assume this is until I see otherwise. And then we have the not lits, which I think is probably just going to, for x1, x2, x3, x4, I'm going to guess that the not lit is going to be like not x1, not x2, not x3, not x4. And then all the things that we are watching is going to be all watches plus not lit. And where did lit come from? It's an unsigned. So I think lit is just one. Okay, so this is not lit is just one, so I think lit is like x84 and then not lit is not x84. And I think watches is saying like, we're going to go over the tree and we're maybe going to ignore certain nodes. I mean, we're going to ignore in general every node except for the ones that are in the watch list. I'm guessing what this is setting up for, but I didn't actually see watches in any of the literature I've read except being mentioned in passing. I didn't see its definition or anything or how it's used. All right, and then we've got the begin watches and the end watches, whatever they are. We'll set star Q to begin watches, and we're going to set star P to Q. So P and Q point to the same thing, which is the watch beginning. And something about the solver being delayed. Maybe this is, I don't know what that's about, but we'll hopefully ignore it. Then we're going to get the size of the watches. This thing about cache lines, the number of ticks will be 1 plus the Kissat cache lines of the size watches, size of watch. Okay. And then some index, which I think index we saw before is just, if you have variables like 1 through a million, the index is just pointing to like what, I guess, variable you're looking at now. So we're passing in lit. So lit was like x87 or something, whatever I said off the top of my head a few seconds ago. So I think that index is now just pointing to like where lit is in memory or something along those lines, or maybe just the value of that variable, like 87. Not value, but like the name of the variable. And then we're setting assigned to assigned plus index, I guess, saying, I think that this is maybe saying like, okay, now assume we have assigned the variable that you passed in here. This is checking probing. This is something about levels, maybe like the level in the search hierarchy. And while P is not at the end of watches, I think P started at the beginning of watches. We're going to set the watch head. Sorry, the head is a kind of watch, and we're going to get it by incrementation. So we're like moving along. Maybe P and Q are like left and right or something. P and Q, I don't know. We'll check the head blocking lit and the blocking value, and whether its type is binary. And then we're going to create a variable for the tail. And if we're not binary, then the tail will be this thing. We're going to increment star Q and increment star P and set them equal to each other. If the blocking value is bigger than 0, we're going to continue. If the blocking value is less than 0, then we're going to say Kissat binary conflict. So this looks more or less like, okay, so blocking value, I was saying that a conflict means everything is false. So I was saying the conflict is necessarily everything is false. I'm wondering if what's going on here is that like that's not actually true, that there could be different assignments that lead to conflicts kind of depending on the structure of the clauses and what the other assignments are. So among other things, if the literal is like, if we have the A, B, and C, A false, B false, C false would be a conflict. But if instead we have A, B, not C, then I don't know. See, it still seems like not C being false would be the conflict, but I'm guessing that somehow what this is doing is saying that like the blocking value is like either true or false, depending on whatever we've computed this thing. And this is saying that like if the blocking value is true, then we're going to continue. But if the blocking value is false, then that's the conflict. And we call Kissat binary conflict. Otherwise, if we are binary and the blocking value is not less than 0, then we assert that there is no blocking value. So I guess it's like a 3-valued logic, true, false, and like undefined, perhaps. And then we call Kissat fast binary assign. And we're going to presumably assign it, passing in a bunch of stuff, including blocking and not lit. And I'm going to guess that it's going to assign not lit to the value from blocking. So basically, since we're assigning not lit, we are presumably, assuming blocking is a thing you don't want to be true, you're assigning the negative of lit, which is logically equivalent to assigning lit the opposite of the blocking value, I think is what's going on, or just a guess. And then we're incrementing ticks. If we're down here, I think that means that we are not a binary clause. I don't know what the other option is, but we've got this arena stuff now. And some garbage stuff, and we're doing more memory stuff. So now, presumably instead of a clause being like a binary, instead of just using binary operations in C, I'm guessing now we're dealing with memory instructs or something along those lines, but probably fundamentally the same. We do get some blocking value, and I think that's really, this is replacement value stuff, but I think I'm just going to really just call it a day here. So I don't know how easy any of that was to follow, but I certainly feel like I have a much better understanding of what the structure of this code is now. And this search propagate is doing both unit propagation and is also looking for conflicts. And then once we find it, we're going to call Kissat analyze. I did say we would look at Kissat analyze, but I'm not sure how deep we're going to get into this. This is just the header. And I believe I can just call C, that C file. Okay, so you're going to pass it a conflict clause. It's checking inconsistency. It's going to start analyze. And I'm just going to look at the names of functions now because I'm in a hurry. But it's going to call things like one literal on conflict level, analyze failed literal, and then some reset analysis stuff. We're going to increment conflicts here. We're going to update tier limits. There's something about whether some minimize and some shrink option. I guess minimize is maybe telling it to reduce the size of clauses or something. That seems to be what's going on here. This is shrinking clauses. I don't know how they're different. And this is analyze reason side literals learn clause. This is presumably going to add it to some sort of clause database. And then we're going to reset the analysis, but not analyze literals. And set result to 1. And then if the analyze, I guess, stack is not empty, is assuming how you would read this, then we're going to bump, and then we may bump the analyzed. And then we might call, I guess, Kissat reset only analyze literals. And we're doing this as long as there's no result. And then if we're down here, then we're going to stop analysis and maybe return a result. Depending, we're going to return 20. I guess if res is less than or equal to 0, otherwise we're going to return 0, which I assume is the success condition, whatever success means here. But let's look at learn clause because that should tell us about how it's keeping the clause database. And again, I guess this is the header. Okay, so it just does seem like we're just keeping things on a stack. So we're going to peek at the stack. We're going to get the size of the stack. We might be probing. I've just been ignoring probing as an additional complexity that I can black box. And if the size is 1, we're going to call learn unit. And if the size is 2, we're going to call learn binary. So maybe binary is not what I thought it was. Maybe binary means we're keeping the variable and its opposite separate, whereas a unit means we're not. I don't know. Otherwise, ref equals to learn ref. So this is kind of doing like a type analysis on what the type of the thing is. But let's look at learn binary. I don't know what not UIP is. I'm just kind of looking at this to see if we're negating the thing. I don't know. But we do have jump level. So we're going to peek at the stack. Looking at the clause, passing in 1, whatever 1 is, and that gives us some other. Jump level, we're going to set the level of other. And then we have a new level that's called by Kissat determine new level. And then we've got backtrack after conflict. And this stuff, I think, is going to tell us where we go after the conflict, just judging from the names. And then we're going to call Kissat assign binary here. And that would be cool to go into, but I don't have time to go into them. And here in Kissat assign binary, we have true lit. I don't see where it's getting the opposite lit, but there is like jump reasons. I don't know. I don't know what binary is. I don't know if searching for binary will tell us. We have dump binary. Maybe binary is just like a 2 clause, a 2 literal clause as opposed to 3. I'm not sure. At any rate, I'm not really going to look into it anymore. That's a second look at Kissat. I feel like I've said, I feel like I have a much better sense of the code, what its structure is. And that's, I think, enough to where if you wanted to then learn about CDCL from a high performance SAT solver, I think you have a good place to start and you can kind of jump into the different parts. I'm not sure that it's probably easier if you're going to look at code to look at a toy solver. And I think that's what people do in competitions. They often have like, kind of like exploration events where you start with some toy solver and like add tweaks to it. But it was interesting, I think, looking at one that's used, I believe, in industry and has performed well in competitions in the past. I'm sure there are all sorts of cool things happening now with LLMs and AI, but this is kind of the classical point of view, kind of pre-AI evolution. Suddenly Bot Eater wants to implement a SAT solver. I think you should. I say do it. And that's all for now. Thank you for joining me on this exploration of the open source landscape. I'll see you again soon.